Hello AP. In the previous lesson we were looking at periodic table introductions with electron configurations and orbital diagrams and valence electrons. Well, now we want to move into the periodic table trends that appear. And there are four of them: ionization energy, electron affinity, atomic radius, and metallic character. Okay, so we're starting with ionization energy, and the definition of ionization energy is simply the energy required to remove an electron, one electron, from a gaseous atom or ion. And so notice the blue equation there. Oops, sorry about that. Notice the blue equation where we see right here the atom, and then it becomes an ion because we've removed an electron. So notice how they make that notation in the equation. So we're starting with magnesium, and we're using magnesium as the example. And so you can see we start out with neutral magnesium and we remove one electron. It takes 735 kilojoules to do this. Now when we go to try and remove a second electron, notice the jump, it almost doubles, and that's because the magnesium nucleus is charged now. It's positively charged, so it's holding that electron much more tightly. And then notice what happens when we try and remove a third electron. The jump is huge. It goes to 7,730 kilojoules. And that's because now we've entered the core. We've entered the full energy level. And so those electrons are held very tightly. Okay, so in general, as you go across from left to right, the ionization energy increases. Okay, and so why is that? Well, that's because the electrons are being added into the same energy level, okay, and so they can't completely shield the positive charge that's pulling on the electron as protons are being added. So what it's basically saying is that as you go across the period, you're gaining more protons, but your electrons are going into the same energy level, so they're being held tighter. They're bound more tightly because of that positive charge that's increasing. The electrons aren't getting further away, so they can't shield the added electrons. Okay? And so when we go down a group from top to bottom, the ionization energy decreases. And why is that? That's because we're adding energy levels, so our orbitals are getting larger and larger. Electrons are much further from the nucleus. But I think when you try and memorize these trends, try and think about the trends always in terms of which direction is increasing. And that way you won't get confused. So ionization energy increases as we go from the bottom to the top, okay, in a group. Okay, so here's a pictorial view for you to see the periods compared to the ionization energies. And you see that as we go, for example, period 2, we go from lithium here to neon, okay? We have a marked increase, of course, because we're going across from left to right. We're gaining protons. We have a marked increase, of course. And then when we go down a group, here's the noble gases from helium on down to radon. Okay, we get a decrease in ionization energy because of those increased energy levels. Now notice that we've got some anomalies, some breaks in the trend. And we'll discuss that with an inserted clip in a couple of slides. Okay, so why do we not have a linear line? Why do we have these anomalies? It has to do with electron repulsions and shielding. And what are some of the exceptions? Some of them include beryllium to boron and nitrogen to oxygen. And so I'll insert a clip here to explain why those anomalies are happening. Okay, let's talk about why we see the anomalies in our trend of ionization energy. Okay, so they listed, let's see, nitrogen and oxygen, okay, and they listed beryllium and boron. All right, now I think the easiest way to explain this is to show you the electron configuration of these elements and then talk about the ideas of electron repulsion and shielding. And so let's look at nitrogen. It's got 7 electrons, so 1s2, 2s2, 2p, let's see, 3, right? Okay, so we've got this going on, and now we hit that p orbital here, and we got 1, 2, 3. Okay, now here's oxygen, 1s2, 2s2, 2p4. Okay, same idea, but now look at our p orbital. 1, 2, 3, and then 4. These pair back up, and what do we know about 2 electrons in the same orbital? Okay, they're going to want to repel each other. So it's going to be much easier to pull this electron out because this one wants to push it out anyway. So that's why there's a drop in the ionization energy of oxygen, even though we're further to the right on the periodic table. Okay, and now if we look at beryllium and boron, beryllium has 4 electrons, 1s2, this is for Be, 2s2, full orbital. Not a full energy level, but a full orbital. Okay, and then we hit boron, 1s2, 2s2, 2p1. Okay, and look at what happens. This is shielding that outer electron, so it's much easier to pluck this one off. These two are full energy levels, and so they're being held pretty tight compared to this one. It's not full. It's easier to pull this out. It's being shielded by these inner electrons. And so there's your explanation for a couple of the anomalies on our ionization energy trend. Okay, here's the concept check. Which atom would require more energy to remove the electron and why? Okay, and why chlorine? Because the nuclear charge is increased. Okay, we're further to the right on the period than sodium, so the nuclear charge is much greater. Okay, let's try another one. Lithium versus cesium, which one would require more energy to remove? That'd be lithium. Why? Because it's closer to the nucleus. Okay, it's only got 1 energy level, and so, well, 2 energy levels, and so it's going to be much more difficult to remove that electron because that nuclear charge is holding that electron much tighter than it would be in cesium further down the group. Okay, how about a larger second ionization energy, lithium or beryllium? Okay, why lithium? Because now you've entered the core. You're trying to remove an electron from a full energy level. Here's a pictorial view or a table, if you will, showing when the core electrons are entered. So you see the staircase showing when the core electrons are trying to be removed. And again, it's showing you increasing. So as you continue to remove electrons from the same atom, the ionization energy increases because the nucleus is becoming more positively charged. And then as you go across the period, it increases. And so remember to try and think of this in terms of increasing instead of mixing both increasing and decreasing together. So flip this arrow around. Okay? All right, second trend, electron affinity. That that term affinity means kind of a desire or a love for. And so what elements do we know that have a love for the electron? Well, we know that the nonmetals have almost full energy levels, and so it just takes one or two more electrons, and they're full, they're stable, and they are um, their electron configuration is complete. And so when they take in an electron, they give off energy as a sign of stability. Okay, and so notice how the equation is drawn here for the electron affinity. Okay, and so when we go from left to right across the period, it's more negative. And remember that negative is just a sign showing direction. So energy is leaving because the nonmetals have a strong desire, an affinity for that electron, and so they become more stable and they release energy. Whereas metals don't really want an extra electron. In fact, they only have one or two in their outer valence shell, and so they want to get rid of those electrons. So to try and give them another one, you almost have to put energy into the atom to get it to take the electron. So that's why its affinities are positive. So you can't really put electron affinity too much into a trend on the table. More so you have to look at it in terms of metals and nonmetals. Okay, and so third trend is atomic radius. Okay, so atom size is going to decrease as we go from left to right, or increase as we go from right back to left. So remember, try and think of the trends in terms of increasing so that you don't get confused. When are we talking increasing? When are we talking decreasing? Just keep it the same pattern. Okay, so why is it decreasing? Why is it getting why is the atom getting smaller as we go from left to right? And that's because as you go from left to right, you're gaining protons, you're gaining that nuclear charge, that effective nuclear charge, but the electrons are going into the same energy levels, so they're being pulled tighter and tighter. It's kind of like a magnet. You're increasing the magnet, so the electrons get pulled in, decreasing the size. And then in general, the atomic radius increases as you go down a group because we're gaining principal energy levels. The orbital sizes are getting larger. Here's a pictorial view for you to see. And again, flip that top arrow around because we want to try and keep this in mind in terms of increasing. So from right back to left, the atom size gets bigger. And from top to bottom, the atom size gets bigger. Okay. All right, which should be a larger atom? Quick check. Sodium or chlorine? And you would say sodium. Why? Because the effective nuclear charge is less than chlorine, so it's not holding those outer electrons as tightly. So it's not squeezing it tight, as tightly. Okay, which atom will be larger and why? And you would say cesium because it's further down in the family. It's gained more energy levels. Its orbitals are larger. Okay, another quick check. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? And you would say the hydrogen 1s orbital because it has less nuclear charge. Okay, right? Only one proton versus lithium's 3 protons. Okay, and then which is lower in energy? Well, the lithium 1s is lower in energy because it has the greater nuclear charge. It's pulling the atom smaller, tighter, so the electrons are closer to the nucleus, therefore greater energy. The further the electrons are from the nucleus, the greater the energy they have.
At room temperature, the metallic element molybdenum exists as a solid crystal. Metallic crystals behave like a three-dimensional array of cations surrounded by a sea of electrons. A molybdenum crystal can be used to estimate the atomic radius of molybdenum atoms. The distance between nuclear centers in molybdenum is 278 picometers, so the atom radius is estimated to be 139 picometers.
Okay, so this video clip was just trying to show you how do they actually get these atom sizes? What do they do to determine atom size? And so they compare the distance between two adjacent atoms, nucleus to nucleus, and then they just cut that value in half. Okay? So in the next clip, another video will show how the gases are measured, or the non-metals, I should say, are measured.
At room temperature, the halogen element chlorine exists in the gas phase. Gas phase molecules are relatively far apart, since gases have low densities. Molecules move in straight lines until they collide with container walls or other molecules. The diatomic chlorine molecule can be used to estimate the atomic radius of chlorine atoms. The distance between nuclear centers in chlorine is 199 picometers, so the atom radius is estimated to be 100 picometers.
Notice, oh, very tiny radius. Okay, slipping past that one, let's try another quick check with this exercise. See if you can arrange oxygen, fluorine, and sulfur into an order of increasing ionization energy and then increasing atomic size. Now remember, ionization energy increases from bottom to top and left to right, and atomic size is just the opposite. Atomic size increases from left to right and top to bottom. Okay, so stop the video and try it. I'm going to show the answers at this point. Okay, so hopefully you were able to look at your periodic table and be able to tell the orders, which ones were increasing in ionization energy and atomic size. Okay, so let's just think about some of the things we've talked about so far. We've discussed the idea that valence electrons are the electrons involved in bonding, so they determine the atom's chemistry. We know that we can write electron configurations or the address of the element from the periodic table, or we could use our cheat sheet that we created. And certain groups in the periodic table have special names, which you'll see in the next slide. Okay, our first group, 1A, is alkali metals. Group 2A, alkaline earth metals. Jumping across, we have 7A, the halogens, and 8A, the noble gases. The elements in the center are transition elements because they have electrons in their d orbitals, which allows them to have more than one charge. And then we have the lanthanide and the actinides, which slide into the transition element blocks. And so that makes our periodic table so much larger. So that's why we pull them out. Okay, so the basic division on the table is that we have metals on the left and nonmetals on the right, and that metallic character tends to increase from right back to left and from top down to bottom. Okay, and here's a visual showing the breakdown of the metals, the nonmetals, and then the metalloids, which are elements that have properties of both metals and nonmetals. The alkali metal group, that family, 1A, they are the most reactive of the metals because they only have one valence electron, which they most readily want to get rid of, and they tend to react with the nonmetals to form ionic solids. The ionic solids also tend to be white in color. Okay, another quick review going down a group. We have an decrease in ionization energy. We have an increase in atom size. We have an increase in density. That's the amount of atoms packed in a certain amount of space. And then we have melting and boiling points smoothly decreasing. Now the melting and boiling points concept, we'll talk about that again when we get into the ideas of intermolecular forces. Okay, and lastly here, the halogen family 7A. This family tends to be the most reactive of the nonmetals because they have 7 valence electrons already, and they only need one more to complete the energy level and become stable. So this is includes our lesson on the periodic table.